In this podcast episode, Dr. Dennis Whyte, a renowned expert in nuclear fusion, discusses the concept of fusion energy and its potential as a clean and limitless energy source. Fusion energy involves fusing together hydrogen atoms to create heavier elements, releasing a significant amount of energy in the process. This process is what powers stars, including our own sun, making it the fundamental energy source of the universe. In stars like the Sun, fusion reactions take place in the core, where temperatures reach around 20 million degrees Celsius. The high temperature and pressure in the core create the ideal conditions for fusion reactions to occur. Gravity plays a crucial role in containing the hot core of the star, preventing the heat from dissipating and allowing fusion reactions to sustain themselves over long periods. To replicate fusion on Earth, scientists use magnetic and electromagnetic forces to contain and heat the hydrogen fuel to the necessary temperatures for fusion to occur. By creating a plasma state where atoms are stripped of their electrons and have a charge, researchers can overcome the electrostatic repulsion between positively charged particles and facilitate fusion reactions. The plasma medium allows particles to interact through electromagnetic forces, increasing the likelihood of fusion reactions. Despite the high temperatures involved in fusion reactions, the amount of fuel used is minimal, leading to inherent safety in the process. The plasma medium prevents the fuel from interacting with terrestrial materials, reducing the risk of accidents. Additionally, fusion reactions do not propagate through a chain reaction like fission, making them more controllable and less prone to runaway reactions. Unlike fission reactions, which rely on a chain reaction triggered by neutrons, fusion reactions occur through a thermal process. The heat released from fusion reactions increases the temperature of the fuel, leading to more fusion reactions. The stable nature of the fusion products, such as helium, prevents them from triggering further fusion reactions, ensuring a controlled and sustainable energy production process. At the high temperatures required for fusion, matter transitions into a plasma state where atoms lose their electrons and become charged particles. In a plasma, particles interact through electromagnetic forces, bouncing off each other without physical contact. This unique behavior of charged particles in a plasma medium poses challenges in containing and controlling fusion reactions on Earth. Fusion energy offers the potential for clean and abundant energy production with the ability to lift people out of poverty by providing low-cost energy solutions. Advances in materials and computational technologies have brought fusion energy closer to commercial viability, with recent milestones showing promise for the future of fusion energy. To convert the energy produced by fusion reactions into a usable form, various methods can be employed. One common approach is to use the heat generated by the fusion reactions to produce steam, which drives turbines to generate electricity. The heat from the plasma is transferred to a coolant, which then heats water to produce steam. The steam is used to turn turbines connected to generators, producing electricity. Another method involves heating the fuel itself, which keeps the system hot and sustains the fusion reactions. Another method involves capturing the neutrons produced in the reactions and forcing them to interact with a blanket material, which absorbs the energy and heats up. This heat can then be used to generate electricity or for other industrial purposes. One of the challenges in fusion energy is achieving a net energy gain, where the energy produced by fusion reactions exceeds the energy input required to sustain the reaction. Scientists are working on improving the efficiency of magnetic confinement systems and exploring alternative approaches such as laser fusion and other containment schemes. By optimizing the density and confinement time of the fuel, researchers aim to create sustainable fusion power plants that can provide clean and abundant energy. While fusion energy shows promise as a clean and sustainable energy source, fission energy is already a reliable option. Fission reactors have been in operation for years, providing a significant amount of energy. However, there are concerns about nuclear waste and the potential for proliferation with fission technology. Fusion, on the other hand, produces minimal radioactive waste and does not rely on uranium or plutonium, reducing proliferation risks. Dr. Whyte's team at MIT has been working on commercializing fusion technology, leveraging advancements in superconductor materials to enhance magnetic confinement. This breakthrough has significantly reduced the cost of building fusion reactors and has opened up possibilities for other fusion concepts. The potential for fusion energy to meet the growing energy demands and decarbonization goals makes it a compelling alternative to fossil fuels. Dr. Whyte envisions a world where fusion technology could revolutionize energy production and distribution. He discusses the possibilities of using fusion energy for desalination, water shortages, and other critical global challenges. He emphasizes the expandability and sustainability of fusion energy as a dominant energy source. Dr. Whyte mentions the integration of artificial intelligence, AI, and additive manufacturing in fusion technology. He discusses the potential of AI systems to optimize fusion plant operations and design processes. He also highlights the role of additive manufacturing in creating complex and efficient components for fusion reactors. Dr. Whyte reflects on the importance of collaboration and innovation in advancing fusion technology. He shares his experiences of working with students and colleagues to solve complex engineering problems and drive technological advancements. He emphasizes the role of universities in fostering innovation and training the next generation of engineers. Dr. Whyte shares his personal background growing up in Western Canada and how he developed an interest in fusion technology, engineering, and physics. He reflects on the intersection of personal interest, conscience, and problem-solving in shaping his career path. He discusses the role of curiosity and passion in driving his work in fusion technology. Dr. Whyte discusses the future prospects of fusion technology and the challenges that need to be addressed to achieve commercial viability. He emphasizes the need for continued research, development, and collaboration to overcome technical hurdles and bring fusion energy to the market. He remains optimistic about the potential of fusion technology to revolutionize the energy sector.